Why do clear photos of the J-35A show it equipped with the WS-21 engine, while military enthusiasts and industry insiders speculate that the fully developed carrier-based variant destined for aircraft carriers will instead be fitted with the more advanced WS-19? Behind this seemingly contradictory approach lies a question: is it due to the Navy's excessively stringent requirements, or is China's aviation industry playing a strategic game, first ensuring availability, then pursuing the pinnacle? Upon examining the starkly different operational environments and urgent needs of the Air Force versus the Navy, we see this is not a simple technical trade-off but a deliberate strategic phased deployment. Its core logic reflects the confidence and maturity of China's aviation equipment development as it transitions from catching up to independent planning. First, we must grasp the Air Force's core requirements for a new medium-sized stealth fighter. With the heavy stealth fighter J-20 already undertaking critical strike and air superiority missions, the Air Force needs a stealth multi-role fighter that can be rapidly mass-produced, cost-controlled, and quickly achieve operational capability at scale. The WS-21 engine is precisely the key component, tailored for this rapid deployment objective. It is not an entirely new model born from scratch, but rather a deeply refined and optimized product based on the highly mature WS-13 series. This means its core design, material systems, supply chain, and even maintenance support systems all possess a solid foundation and extremely high reliability. For the Air Force, the thrust and performance delivered by the WS-21 enable the J-35A to excel in the vast majority of predefined combat scenarios. It provides stable supersonic cruise capability, excellent range and payload capacity, while keeping production costs and operational maintenance burdens within ideal parameters. The primary objective of pairing the J-35A with the WS-21 is to rapidly increase flight hours, accelerate unit deployment, training, and tactical system development, and integrate this cutting-edge equipment into the overall combat system as quickly as possible. Recent leaked photographs corroborate this, revealing meticulously machined, uniformly coated nozzle serrations that indicate the WS-21 and its stealth treatments have entered standardized mass production, the material foundation for rapid deployment. However, the environment and challenges faced by naval aviation are entirely different, even demanding. Carrier-based fighters take off and land on the undulating deck of an aircraft carrier, subjecting their engines to extreme tests unimaginable for land-based aircraft. During catapult launch, the engine must instantly deliver maximum afterburner thrust to propel the fully fueled and armed fighter like an arrow from a bow. Conversely, during aborted landings requiring immediate takeoff escape maneuvers, the engine must demonstrate remarkable residual thrust response capability at low altitude and low speed, a capability directly impacting the pilot's and aircraft's survival. Moreover, the marine environment's high salinity, humidity, and corrosiveness pose immense challenges to the durability of engine blades, hot-end components, and internal precision systems. These harsh conditions demand top-tier performance and thrust limits, response speed, reliability, and environmental adaptability. Clearly, the WS-21, a deeply modified variant of land-based engines, though mature and reliable, may be nearing its performance limits when confronting these uniquely demanding naval challenges. In contrast, the WS-19 engine, developed specifically for next-generation medium-weight fighters, is a fourth-generation medium-thrust turbofan designed from the outset to meet carrier-specific requirements, with a higher target thrust-to-weight ratio and significantly enhanced maximum thrust. Not only will it provide the J-35 with more abundant thrust, ensuring it can operate with ease on aircraft carriers, even at maximum combat weight during takeoffs and landings, thereby carrying more ammunition or flying farther, but its materials and protective technologies will also be reinforced against maritime factors like salt spray corrosion. Therefore, for the Navy, the weight for the WS-19 represents the acquisition of a truly complete carrier-based power core. This ensures the J-35 can deliver 100% of its designed combat capability, and potentially exceed it, in the open seas, amidst the most complex electromagnetic countermeasures, and under the most intense combat conditions. This is akin to selecting a propulsion system for a long-term, high-risk maritime expedition. Both stability and peak performance are indispensable. The choice must be the flagship engine, built specifically for stormy seas and boasting the most abundant power reserves. Looking back at the development of China's aviation equipment, this strategy of prioritizing platform development while gradually advancing propulsion systems is not unprecedented and has proven to be a pragmatic and efficient path to success. The J-20's evolution serves as the prime example. It initially used Russian-made engines for its maiden flight and early test flights, swiftly validating its aerodynamic and flight control platform. Subsequently, it transitioned to the domestically produced WS-10C Taihong engine variant, enabling large-scale deployment and achieving initial operational capability. The ultimate goal is to equip it with the more powerful WS-15MI engine, unlocking its full performance potential. The J-35 program clearly draws upon and refines this approach. By equipping the Air Force variant with the mature and reliable WS-21 first, it rapidly achieves deployment scale, cultivates seed instructors, and explores tactics and combat methods, while simultaneously accumulating vast flight hours and operational data for both the engine and the entire aircraft. Concurrently, the Aero Engine R&D team can focus entirely on overcoming the final technical hurdles of the WS-19, conducting the most rigorous testing and validation. Once fully matured, it will then be deployed on the carrier-based J-35 variant, which demands the most extreme performance capabilities. This approach enables parallel progress across multiple fronts: equipment deployment, personnel training, tactical innovation, and power plant upgrades. It significantly compresses the overall combat capability generation cycle, avoiding the predicament where advanced fighter platforms sit idle while waiting for a perfect engine. At a deeper level, this strategic choice reflects a closer, more flexible interaction between China's aviation industry and military users, as well as an overall enhancement in strategic confidence. In the past, we might have reluctantly delayed aircraft development or accepted performance compromises due to engine limitations. Today, we can deliver off-the-shelf engines like the WS-21 that meet performance standards with high reliability, while also having the confidence to develop bespoke engines, like the WS-19 for branches with higher demands. This capability is underpinned by robust technological reserves, a comprehensive industrial system, and clear strategic planning. The Navy's exacting standards for engines reflect its exceptionally high benchmarks for future maritime combat capabilities. The industrial sector's ability to meet these demands demonstrates a significant leap in capability. Together, they propel equipment toward world-class standards. In summary, the WS-21 powering the J-35A and the anticipated WS-19 for future carrier-based variants represent not a hierarchy of superiority but distinct roles. The WS-21 serves as a pioneer and foundation builder, tasked with rapidly deploying and integrating the J-35 family into the PLOF's operational framework, while refining the platform and cultivating talent. The WS-19, however, is the climber and the ultimate performer. Its goal is to equip the blade between sea and sky with the most powerful heart, ensuring it possesses peak performance to match any formidable adversary on the most critical front lines of national interests, the most challenging aircraft carrier deck. This dual-track propulsion strategy embodies the ingenuity of China's aviation equipment development. It balances the urgent demand for combat capability with the long-term pursuit of technological supremacy. Through a systems engineering approach, it achieves the optimal equilibrium between speed and quality, scale and peak performance, ultimately serving one overarching goal: to ensure the J-35, this stealthy blade, can unleash its most decisive power whenever and wherever it is most needed, whether on land or at sea.